this is why when we have this matrix, we know lambda 1 is 0, lambda 2 is 2. If you take this matrix to the kth power, I mean, you guys all should know, like, if you take a diagonal, multiply two diagonal matrix, what happens, right? If you multiply two diagonal matrices, just the diagonals gets multiplied. So this to the kth power is the same as lambda 1 to the kth power, which is 0, lambda 2 to the kth power, which is 2 to the 100, right? So the matrix, right, to the kth power is equivalent, I mean, has a magnitude of 2 to the 100, or whatever eigenvalue it has to the 100, okay? As long as when you multiply a vector, and the vector doesn't get 0 when you multiply this, as long as the vector doesn't get 1, 0, so basically the big one, the lambda 2, that is large, as long as this one is not multiplied by 0, you're going to get a huge vector. Okay. So we know that, going back to here, right? So we know that if I have a matrix A, and A has an eigenvalue that is equal to 2, we expect an amplification of error, despite what the other eigenvalues do. I mean, if I have other eigenvalues that are, no matter what it is, as long as it has an eigenvalue equal to 2, you expect trouble. Yes?
Would that be true for any eigenvalue larger than 1?
Yes, the question is, can I generalize this? Is there a criterion for the eigenvalues of matrix A that can determine if this formula is going to get me a huge error at the end, or it's going to get me an okay error at the end if my initial error is time? We know if it's 2 is trouble, right? Actually, I'm gonna give you another matrix that's a little bit more interesting. How about this +1? Am I expect to get trouble for that? I'm glad you are now doing eigenvalue calculations. Good. Am I supposed to get a huge error at the end if I have a matrix like that? Okay. Anyway, I know you are doing calculation. This is something a little bit more difficult than the previous one, because the eigenvalue you get is going to be complex. It's not going to be a real eigenvalue. But like, let's actually see. And before we answer this question, you may put it in the back of your mind. Let's see, how does this have to do with the scheme that doesn't work? I mean, there is no matrix here, right? How do I analyze the magnitude of these u's just with one equation as opposed to a matrix equation? Any suggestions? Yes? Yes, can try that. It's gonna be a diagonal matrix. Don't see how. The idea is actually very similar to the first lecture we have, maybe the second lecture, how we actually turn the second order ODE into a first order ODE.